Okay, let's move on to the last talk today. Welcome, Professor Weijie Su from University of Pennsylvania. The title of his talk is A Statistical Viewpoint on Privacy, from the 2020 US Census to Hypothesis Testing to Blackwell Theorem. Welcome, Professor Su.
Yeah, first of all, it's my tremendous honor and privilege to stand in front of here to give this talk. And so my talk will be differential privacy, and our focus will be on its application to the US Census in 2020. Okay, so privacy has been becoming a really concern because nowadays this big tech has ability to collect our data on a live basis. Basically, they know where you are, right? Where you are traveling, which restaurant you are visiting. Yeah, okay, they know everything about us, so basically. And so this is an example about how privacy could be violated. So this is the Netflix competition. So here, basically everyone, okay, watch a movie. If you watch a movie, you can rate the movie from 1 to 5, okay? But for most of movies, you didn't watch, right? So it's a question mark. So this Netflix competition is required to based on these existing ratings to reserve to predict these unobserved ratings. Okay, but however, in the second year, so this Netflix competition was canceled. So it's really because people, by relating the Netflix dataset and another dataset called IMDb, people can identify some user. Okay, although these users' name were anonymized. So this means that anonymization alone doesn't work. Okay, doesn't work. Okay, and then how about releasing summary statistics? Unfortunately, summary statistics means that, okay, I don't really tell you all the individual data point. I just tell you the average, okay, average sum. However, this is not the case. And so in 2028, Homer and several people showed that actually, if you just release the average of the minority frequencies, okay, to basically tell you that how frequent this gene is, okay, across many genes from this data set. And then it's possible to identify whether a specific user is in the data set or out of the data set. Okay, suppose this data set contains people of diabetes. Okay, this violates privacy. And so this really changed the practice of how NIH require people to release information. Okay, looks like it's the end of privacy, right? There's no privacy anymore in the future. And but can we really give up privacy? So the short answer is perhaps no. Okay, it's really because, for example, so Peggy Noonan, who was a well-known journalist and a novel writer in the U.S., so her has a paper article on Wall Street Journal. So she said that a loss of privacy is a loss of something personal and intimate. Okay, it's something we cannot bear. And the Nat Hentoff was an American Constitution. So he basically argued that privacy is an American constitutional liberty right. Okay, and you can of course replace American by any other country, I believe. Okay, so now let's start. Actually, this is how I jumped into the field of differential privacy research. Okay, it was in 2014. By then, I was in my third year PhD. So I spent summer as an intern with Synset work in Microsoft Research in Silicon Valley. So Synset work was as you will see, is the inventor of one of the co-inventor of differential privacy. Okay, so the idea of differential privacy, is, roughly speaking, is that we want to ensure that we cannot identify whether it's Alice or Hua Mulan in the dataset. Okay, you cannot tell whether it's Alice or Hua Mulan, and assume that all the remaining. So suppose there are 1,001 individuals in the dataset. Okay, and then let's fix the 1,000. Okay, the 1,000 dataset is fixed. 1,000 data points, 1,000 individuals are fixed, but you don't know whether it's Alice or Hua Mulan. And what you do is basically add some noise on the output of the algorithm. And based on the output of the algorithm, you cannot tell it's whether it's from Alice or Hua Mulan. So that's the essence of differential privacy. Okay, so this is a VisionNet. And so here, each row corresponds to an individual, okay? Alice, Bob, Charlie. And each column corresponds to some features. Some features are, okay, can be public, some a little bit sensitive. And so an example is basically, for example, if you want to release the average salary, okay, and you have to add the noise. the noise should be basically right at stem level about the difference between different people. If the noise is small, then I can tell whether it's Alice or Bob. If the noise is large, then it's too noisy, right? The statistic is not that useful. Okay, so this is the definition of differential privacy proposed by Cynthia Dwork, McShaffey, and Colby Nissim, and Adam Smith, roughly 20 years ago. So differential privacy basically requires that the output of the algorithm as a probability as a random variable. Okay, and this event, actually the probability is basically very similar to the probability if it's to when Alice is replaced by Hua Mulan. Okay, and when data is zero, okay, data is zero. Of course, in practice, delta is very small. If this is exact zero, then we require that the likelihood ratio between Alice and Hua Mulan is bounded away from e to the power epsilon. Okay, in this definition, epsilon and delta are two parameters, non-negative. The smaller, the better. The smaller epsilon or delta is, more privacy guarantee we get. Okay, so we want to make sure that the epsilon delta is either is small. So now there's a really impact about differential privacy. So it has been used. Okay, so maybe it's small. So this is a screenshot of my own iPhone when I was asked to upgrade my iOS system, and it said that okay, do you agree to upload your data to iCloud for analysis, and they will use differential privacy to guarantee my confident privacy. So I said yes. Okay, this is my first time actually I learned about. This actually, it was a really a moment for me because I was working on different privacy, but I saw that okay, different privacy is really was used in practice, and so later different privacy got so the 4 authors received the Goldel Prize in computer science, so which is the highest recognition in theoretical computer science. And in 2020, okay, so this is a big moment for differential privacy. In 2020, so the census, the US Census Bureau, for the first time in history, use the differential privacy to make its statistic census data private. It's the first time. So now let's go to the what's new part of the talk. Okay, so this joint work with first is based on this paper. So this is joint work with Bu Xingsu, and he's still at Penn, and Chendi Wang, and he has left Penn for Xiamen University. So this is basically the US Census Bureau, how they, it's a rough illustration, okay? So there are different levels, okay? For example, from the US level, the national level, to the state level, and up to the block level. And they will release basically at least 10 different queries, 10 different statistics, 10 data points about for each level, okay? So now we want to import differential privacy, right? But we need to recognize that actually here, every count is basically an integer. For example, and if this is denotes, for example, the region in, for example, in New York, okay? New York City or New York State. And we want to count how many people are above 18 years old. So this is an integer, right? This is integer value. And then we want to add a discrete Gaussian noise. So what is discrete Gaussian noise? Discrete Gaussian noise is basically just Gaussian noise, but it's supported on integer values. Okay, and otherwise you see basically the probability density is the same as the Gaussian function, but now we have a different normalization factor. Okay, so here difficulty is that actually for each level, there will be 10 different queries, okay? 10 different queries about, for example, how many women, how many are minorities, 10 different queries. So it's a composition at each level. So that's a difficulty, how the difficulty could come from. And so in 2022, when the census finished its census, they wrote a paper, and in particular, there is an open question asking experts on differential privacy to solve. So this question is about, is it possible to make sure to get a stronger privacy guarantee than what the Census Bureau has pretend? Okay, so why this is important? So this is important because if we get a stronger privacy guarantee, so this means that actually we can add slightly less noise, right? Because this essentially shows that there could be a better privacy and utility trade-off. When you get a better trade-off, okay, then you can slightly sacrifice privacy, but this after sacrificing the privacy is still at the level you can tolerate. Okay, still good, but you can add less noise. By adding less noise, and you will improve the utility. Your census count will be more accurate, will be better. And why having more accurate census count is important? It's really because census is perhaps the U.S. census data is perhaps one of the most important data sets in the world, I guess, because census data is used for federal funding distribution, is for redistricting, and also for apportionment of congressional representation. So this basically has a huge impact on the U.S. political science and economy. Okay? So that's why having a more accurate census count is crucial. Okay, so this is our results. So our results, okay, our result basically shows that using our method, we basically can answer the open question affirmatively. And our answer is that yes, we can actually get better privacy guarantee and uniformly across any level, from the national level up to the block level. So here we basically fix the data again for a fixed data, and the smaller value of epsilon is, better privacy is. Okay, so for example here, so this is the privacy guarantee by the Census Bureau. Okay, but what if we can prove that actually the real privacy, the real value of epsilon is 4.47, is smaller than 4.79. Okay, and this is uniformly across different levels of US to the US level to the block level, and for different values of data. Actually, this is a mathematical theorem. We can prove that for any level, for any value of data, we can always get a smaller value of epsilon than what the Census Bureau got. Okay, so this is the mathematical theorem. And in practice, we can show that we can basically reduce the value of epsilon by 15% or 10 to 20%. So this is something we can get for free. And since we get a better privacy guarantee, right? So then we can add less noise to match the original privacy budget. So this is basically the noise level required by, for example, the Census Bureau, so that they need to add this amount of variance of noise to ensure privacy for the US level. But what if we can prove that actually we only need 54 as noise level? So we can reduce the noise variance by 14% in this case. So basically it ranges from 14% to 17, 18%. So this is basically we can always get, and we can get noise reduction for free, but while maintaining the same privacy guarantee. And so the improvement is more pronounced if we go to the more downstream task. Okay, so here is basically we want to do a regression based on the proportion of individuals which are educated and to predict the median earnings. And so basically we get a regression, okay, linear regression, simple linear regression. And then what we can prove, we can show that using the method of the bureau, using our method, we can basically reduce the mean square error by a lot, maybe half, even more. So it's a really significant improvement. Okay, so now let's introduce our method. So far, everything is basically we only have presented the method, the results. We haven't shown you how we achieved the thing. Okay, so defined privacy can be formulated as a hypothesis testing problem. Okay, so basically we want to distinguish. We want to tell whether it's Alice or Bob in the dataset, right? Alice or Bob, or Alice Annie. And for the other people, individual Bob to David, they are the same. The only difference is between Alice and Annie. So basically, we can formulate this as a hypothesis testing. On the null hypothesis is Alice. On the alternative is Annie. Okay, and so basically this, and if the intuition is that if this hypothesis testing is very easy to test, okay, you can easily tell whether it's null and alternative, then there's no much privacy, right? If this is very difficult to tell them apart, then privacy is well guaranteed. So this is the essence of defined privacy. And based on this thing, actually, we propose a new privacy guarantee framework called the f-differential privacy compared to epsilon delta defined privacy proposed by my mentor since at the work at all. Okay, so basically, first of all, they are both using hypothesis testing formulation. Okay, first of all, this is the same thing. But we are using the type 1, type 2 errors trade-off. okay, as our metric, but they are using the what's likelihood ratio absolute delta. And so as a result, our parameter is a function between 0 and 1, but their parameters are just absolute delta. So the typical way for us to treat privacy is to add the Gaussian noise, but for the absolute delta, it's basically to add the Laplace noise. Okay. So this is a paper and the courses, and so Jing Shuo, and he now has returned from Penn, did a postdoc at Northwestern University. Now currently he is at Tsinghua, the Yale Math Center. And also my colleague Aaron Ross from the CS department of Penn. Okay, so this paper was accepted as a discussion paper and was read to the Royal Society in the UK. So last year we were very lucky. We got a paper award from the ICBS conference for this paper. Okay, so now let's record that it's the hypothesis testing formulation, right? And we can define the type 1, type 2 errors. And so type 1 error is defined as in reality is any, right? Alice, but you mistakenly classify this as any, okay? From Alice to any. So this is a type 1 error. So type 2 error is the opposite. In reality is any, but you think this is Alice. So from Q to P. So this is a type 2 error. Okay, and so then we can define the trade-off function between P and Q. Okay, P is basically, let's denote P as a probability distribution of the output of the algorithm if the reality is Alice. Otherwise, it's Q. So the probability distribution between P and Q, we can define the trade-off function. The trade-off function defined as for any value between alpha, between 0 and 1. So this is the smallest type 2 error such that the rejection rule is still control the type 1 error at alpha. So because of the Neyman-Pearson lemma, we know that this is can be achieved. So basically this can be identity, okay? And so there must be some phi such that the type 1 error is exactly equal to alpha and achieve the minimum. So here the infimum can be replaced by mean. Okay, so this is our definition. So we define that an algorithm or method is to be f-differential private if for any neighboring data sets, for any S and S prime, if they differ by only one individual, meaning that they only differ by Alice or any, and their trade-off function is lower bounded by F. So a lower bound on the trade-off function means that the type 2 error should be large enough, right? So this means that it's difficult to distinguish between Alice and any. So privacy is better. So there's strong privacy. So here the randomness comes from the method M. So it's not from S. So this is a little bit departure from the conventional statistical thinking. In statistical thinking, we often think that all the randomness comes from the data, right? But here, the randomness comes from N, the method, okay? The method, the algorithm. Okay, so this is let's record the definition of absolute data differential privacy. So basically, we require that the probability distribution, the density between S and S prime, Alice and any should be very close to each other. Okay, should be very close to each other. And so a result due to Weissman and Jill showed that actually absolute data differential privacy is a special instance of our FDP. Why? In this case, this F function can be chosen this way. Okay, a little bit ad hoc, right? Ad hoc, but yes. So this shows that F differential privacy includes absolute data differential privacy as a special example. This is a motivation for our work, right? For our work, because think in general, F can be any convex function, right? Below this 45-degree line. But why should we choose this such ad hoc function parameterized by absolute data, right? In general, F can be anything, right? Can be any convex function. So this motivated our work to extend this absolute data differential privacy to a general framework. So now let's try to be more specific about F. So a parameter actually is central to our definition is called GDP, Gaussian differential privacy. So here it's parameterized by mu. So essentially we want to distinguish between a pure Gaussian noise with mean mu. Okay, you see if mu is large, right? Mu is larger than 3, then you can easily tell they are different. But if mu is smaller than 1, for example, it's hard to tell them apart. And this definition for this definition, if we let f to be the trade-off function to be this trade-off function, okay, we call it mu GDP. So this is a special instance of FDP, just like epsilon delta. But why is this important? We will show later because of the central limit theorem phenomenon. So first of all, let's show the curves for different values of epsilon, of mu. Okay, when mu is a half, okay, this is quite private, okay, very close to this line. This line is basically twice a coin, right? Basically, type 1, type 2 errors add up to 1. But when mu is 6, okay, it's basically the same as this x and y axes. There's no difference as well. You cannot eyeball the difference. Okay, in general, how can we achieve different privacy? So the idea is very simple, add noise. So add noise. So this is universal template, okay? And you give me a statistic and I add noise to it, and then I can ensure privacy. So there are many templates, of course. And one of the most universal, popular template is a Gaussian mechanism. It's basically add noise to your statistic. How much noise should I add? Depends on, for example, the sensitivity. Sensitivity means that how much perturbation you will see in this statistic if you replace Alice by Annie. So this is the perturbation perspective. Okay, so now let's try to take a look at this FDP from a information theoretical perspective. So this is a paper I wrote for this journal annual review of statistics and its application. Okay, so basically, first of all, what is post-processing? Post-processing means that given some output from an algorithm or method, and you further apply another method to the output. And you see, so basically this is a self-evident that if you make some further processing on the output of the algorithm, you only make the algorithm more private, right? More private. So this is an axiom in our view. Axiom. So if an algorithm M is private, then its post-processing should also be private. And then we can first show that our FDP satisfies this post-processing. It's really because, okay, and P and Q are two distributions, and we apply some post-processing, for example, do dimension reduction for projection, okay, whatever. And then the trade-off function will only be larger than the original trade-off function, meaning that the type 2 error will get larger for any level of type 1 error. And this is a theorem. And the theorem, actually, the proof is easy, but the interpretation, I would say, is fundamental and profound. So this shows that any DP, different privacy definition, which satisfy, okay, the post-processing condition, which is the axiom, and then the privacy metric must be defined through the trade-off function, must be defined through some link function D. Okay, and in this sense, FDP is the most informative, right? Because it's just use the original trade-off function without any without losing any information from the trade-off function. And so there are some examples of epsilon delta dp and epsilon delta dp, and they use different such metrics between p and q. This can all be expressed as a link through a link function D. Then how to prove it? Actually, this is a remarkable theorem due to David Blackwell. So David Blackwell was the first African American who got a PhD in mathematics. So he wrote a paper basically titled "The Comparison of Experiments," and of course he used different terms. We translate his terms to our language. So basically, what we can show what David Blackwell showed 70 years ago, right? Basically, is that this A and B, the two statements are equivalent. So if the pair of P prime, Q prime, okay, the actual function is larger than P and Q, and then it's equivalent to that P and Q prime, P prime, Q prime can be derived from PQ by a post-processing, and vice versa. So this is why this theorem implies our previous theorem. This is really because you see, if they are equal to each other, right? If they are equal to each other, the function are equal to each other, and then P prime, Q prime must be derived from PQ, and vice versa. So this means that there would be a one-to-one mapping between PQ to P prime and Q prime, one-to-one mapping. And then information theoretically, they are equivalent. There's no difference at all between P and Q. And recently, and it's a remarkable thing, NVIDIA, Jensen Huang, NVIDIA announced last year, I think, that they will use Blackwell to name their next generation chip system. So this is to honor, okay, a great African-American mathematician. Okay, so but however, there are many other divergence actually is not complete. Okay, it's not like trade-off function. For example, this is a Rayleigh divergence. So Rayleigh divergence is defined this way, right? When gamma is one, this is a KL divergence. But however, we can prove that for these Bernoulli distributions and in terms of the Rayleigh divergence and the Bernoulli distribution is closer than the normal distribution. But however, if you take a look at from the total variation distance perspective, it's not the case. And look, in A, actually this holds for any value of gamma larger than 1. So this means that actually the Rayleigh divergence perspective will violate the perspective of other divergence. So it's not complete. It's not self-consistent in this way. But this is not the case for trade-off function. For a trade-off function, if one pair is larger than the other, and then any other trade-off function, any other divergence which obeys post-processing must satisfy the same ordering. So it's complete. So mathematically, it's complete. Okay. So now let's go to the second part, composition. So composition here is a fundamental in differential privacy. Why? Because if I ask more questions, I do more analyses, and finally I will end up knowing more about you, right? More about you, then your privacy will degrade. So any privacy definition and privacy framework need to answer how your privacy will degrade if you do more composition. Okay, so then essentially we can make composition as an algebra in the framework of f-differential privacy. So roughly speaking, okay, and the first algorithm M1 is FDP and the F1DP, and for the second algorithm is F2DB. Okay, then essentially you can do a composition between the first algorithm and the second algorithm. Okay, you make them together. Okay, so this is, for example, this is your height, this is your weight. I can concatenate more and more, and so this is the algebra. Also, we define the so-called tensor product between two trade-off functions, f and q, and f and g. F is the trade-off function between p and q, and g is p prime and q prime. And then we define the tensor product between f and q, which is another trade-off function. Is defined as the trade-off function between p times p prime versus q times q prime. So in the case when PQ are just normal distribution, and then it's essentially still normal distribution, and the parameter will be basically the L2 norm of each component from mu1 to mu k. Okay, by the way, so this definition is well defined. It's commutative and associative. It's mathematically it's well defined. Okay, so this is a simple algorithm, simple theorem shows that if each f method is FIDP, and then together the composition will still be FDP, and this f function will be the tensor product of all the small functions. Okay, small functions. Okay, so this cannot be improved in general. So this essentially makes the composition under FDP essentially an algebra. So it's closed. It's closed. It's well defined. Okay, so this is a central limit theorem. So this shows that for each algorithm Fi, suppose it's still almost private. Okay, you only lose a tiny bit of privacy. Okay, but suppose the number of steps you need to do under this algorithm is large. It's very large. So essentially, you need to do a very large number of composition. Okay, but each one is small. You only validate a tiny bit of privacy, and then the total budget, total privacy, okay, loss you will lose. Essentially, will be given by Gaussian differential privacy, and this mu actually will uniquely depend on the first and the second moments of each of the trade-off function. So this is a central limit theorem. Of course, the theorem does not look like a central limit theorem, right? But proof actually is just following the central limit theorem. Why? Because you can just look at the likelihood ratio between P and Q, okay? And you look at the likelihood ratio, the sum of the likelihood ratios under the P, under the null versus under the alternative, and you look at the difference between these two, then it's a proof. You just can apply the central limit theorem, get this result. Okay, so the interpretation of this theorem is very useful. This means that, okay, the competition of this thing is very complicated, right? But however, now you can reduce the competition to a single parameter. Once you know mu, basically know everything. So this makes the approximation much easier. So it's basically a approximation tool. Okay, so this is approximation. Okay, and here the number of folds is just 10. Even with a tenfold composition, you see, and our approximation, which is indicated by blue, is already very, very close to the red exact composition. Okay, but if you are using the epsilon delta approximation, you only get this. Okay, so you see this is a large departure from the original exact value. Okay, so this means that our FDP has the more flexibility to approximate the true ground truth privacy. So now let's talk about subsampling. So subsampling is another important fundamental operation in privacy. So it means that if you are dealing with a huge data set, you don't need to apply your algorithm to every data point in the data set. For example, you only need to subsample maybe 1% or 10% of the data points apply your method. But suppose the subsampling rate, which is denoted by P, okay, suppose P is 10%. So this means that 90% of the time, you are not selected for analysis. So 90% of the time, your privacy is perfect. Okay, it's perfect because you are the analysis is not applied to you. Then your privacy is, of course, is not violated at all, right? So now let's study how privacy will enhanced if we do such subsampling. Suppose we let P to be 10%. Okay, and what we can prove that actually is that okay, and FP is the convex combination between P F and 1 minus P identity. So this is a probability that actually you are not selected for analysis, which means perfect privacy. Okay, and now let's swap the X and Y, make it more symmetric, and consider the mean. So this is a convolution, which is the double conjugate of the function, which makes it convex. Okay, so our theorem we can prove that actually, if the original F is FDP, and then the subsampling of the subsample. Okay, this is still FDP, but this trivial function is replaced by this operator. So it's an operator on the original trivial function. So now let's look at the illustration of this result. Okay, and this is the original privacy. Okay, original privacy guarantee. Okay, look, the higher the trivial function, the better privacy guarantee. Okay, so this is the privacy guarantee what we get using our red. Okay, so you see, the improvement we get is this region. Okay, the original privacy analysis only gets this result, this trivial function, but what we get is this one. So this is a region we gain by using our privacy framework. Okay, and so I think I have 15 minutes. Okay, I know, which is good. Good enough. Now let's just consider a small vignette application. Just apply our privacy framework to private deep learning. Okay, you see, private deep learning is fundamental, right? Your private deep learning is where you use, for example, face recognition, and for example, even in large language models. And so it's important to make it private. Okay, but however, in the training of differential deep learning models, is essentially is a two parts. One part is basically subsampling. Each time you need to subsample maybe 100%. Or maybe 100 images to compute your mid-batch gradient. And then you need to do this for many, many times. Okay, you need to do for iteration for millions or for billions of times. So essentially, it's subsampling plus composition. Since we have already a privacy analysis for subsampling and the composition, and then let's apply our theorem together to get a privacy analysis for deep learning. So this is our bond. Okay, so basically we can show that for private deep learning, under our FDP framework, and then the total privacy loss will be mu GDP. And this mu is given by this thing. Okay, look, so here T is the number of iteration, right? Of course, if the number of iteration is larger and larger, and you will have mu will become larger. A larger value of mu means less privacy. But however, you can make, for example, make a sigma, the noise level you add, larger. Okay, if sigma is larger, so this value will be closer to 1, will be smaller. So this is what you can do to counter a large value of iteration T by setting sigma to be larger. Okay, so this is our result. It's a comparison with Google Brain's approach. So this is the privacy analysis on training a private deep learning model on MNIST. So our privacy analysis is given by this blue line, okay? And this is the privacy analysis by Google Brain. So basically, you can see that our analysis is uniformly better than what Google Brain can get, okay? So, and we can actually see that the improvement is even more significant when the accuracy is larger. Okay, in this case, so this is the privacy analysis. This is privacy analysis by Google Brain. Okay, so basically by this you see there's no privacy at all, right? There's no privacy at all. You can basically make a type 1 type 2 error to be 0, easily to distinguish between Alice and Annie. But actually, what we can show that actually the privacy guarantee is still decent by our red line. Actually, the mu actually between the standard normal distribution, here the mu is just within 1 standard deviation. So this means that actually it's still there's still decent privacy, okay, there. But however, if we look at the epsilon value using Google Brain's approach, epsilon here is 7.1. 7.1 means that each of the 7.1 is more than 1,000, okay? So this means that the likelihood ratio is more than 1,000. When the likelihood ratio is more than 1,000, the two distribution must be very different, right? So this means that from the Google Brain's analysis, there's no privacy at all. Okay, and since we get better privacy, and then we can add less noise to match the same privacy guarantee given by Google Brain. And by adding less noise, and we can get better privacy prediction, test performance. And so this is the test performance. This is accuracy of our results. Okay, it's uniformly higher than that of Google Brain. So now I have 10 minutes. Now let's quickly give the proof sketch of how can we use our FDP to enhance the privacy analysis for the 2020 US Census. Okay, so basically this is the original the Census Bureau's method. Okay, you just compute the epsilon data curve basically. But what do we do is do a detour. What we do is first we formulate this as a hypothesis testing problem. Okay, and then we numerically compute the trade-off function. And once we get a trade-off function, we finally translate everything back to epsilon data. Okay, so this is a detour. So this is a difference between our US census method and our method. Okay, so now this is hypothesis testing formulation. Okay, now we know that for the Census Bureau, they added discrete Gaussian noise. So this Gaussian noise is basically to support the Gaussian distribution on integer values. So it's basically integer, discrete, okay, discrete. And so this is the original mean. So this is the mean with some perturbation, maybe to perturbed by 1, okay? Okay. So the difficulty comes from the discrete thing. It's discrete. If this is Gaussian, if this is too Gaussian, then this problem is trivial. But since this is discrete Gaussian, the problem is much more difficult. So now let's first use the Neyman-Pearson lemma. So Neyman-Pearson lemma allows us to summarize everything through the likelihood ratio. So P and Q, small p and small q denotes the probability density function of the big Q and the big P and the big Q respectively. Okay, so basically we can define the likelihood ratio between Q and the P, but under either the null distribution or under the alternative distribution. Okay, so although they are mathematically they are defined the same form, but since the underlying distribution x and y are differently distributed, and then Cassie and the data are two different random variables. So essentially, we can basically, this is a theorem, or actually it's essentially a lemma. We can define express the value of data through epsilon as a function, as a difference between their two tails. So this is a tail of the sum of the data values larger than epsilon. So this is the tail for the Cassie. Okay, and e to the epsilon times e to the epsilon. So this difference essentially gives the value of data. Okay, so you look. So basically, these two terms are the same. The only difference that they differ by a constant. Okay, differ by a constant. So this means that essentially we only need to evaluate this probability, this tail probability. If we can evaluate this tail probability, then we are almost done, right? So essentially, we want to evaluate the tail probability that each xi, each random variable is a discrete Gaussian, and then how does their tail behave for their sum? Okay, if each is a original Gaussian distribution, of course this is trivial, right? Because essentially the sum is still Gaussian distribution, normal distribution. Of course, it's trivial. But the difficulty here is that every term is an integer value. Your outcome is still an integer, but it's no longer discrete Gaussian. Discrete Gaussian is not closed under summation. Okay, so this is for the case when it's homogeneous, meaning that each sigma I are equal to each other. In this case, it's simple. It's very easy because we can leverage the local CLT type results. So basically, the tail probability, okay, and we can sum this as for different values of integer, okay. T here must be an integer, and then this is essentially a scaled version of the original probability density function. But difficulty here comes. Yeah, here's the approximation. The approximation is very sharp, it's very accurate. So so the original result is given by this blue, okay, and our approximation is given by this brown curves. So this is the approximation bound, okay. What we can prove that for any value, basically for any value of number of competition. So this is when for different values of the sigma, okay, and this is the approximation error. Our approximation error here, especially when sigma is large, is essentially smaller even than the numerical machine precision. Okay, it's very small. It's much smaller than what we need. Okay, so it's sufficient. But the difficulty here comes from when the case is homogeneous. Homogeneous means that, okay, now from the national level to the block level, we may add different noise levels. Okay, then the problem becomes more difficult. So in this case, now it's essentially still a lattice, but now it's a lattice of maybe some with a fraction, some with maybe even irrational factor in front of it. So it's a mix of lattice. The problem becomes much more difficult. So I don't have time to explain this method, but what we can basically show that what we basically do is basically to use a hybrid method. So basically, we approximate the probability distribution using a characteristic function. For the main term, we basically use a closed form expression. But for the remainder term, we resort to numerical approximation. So finally, we get what we want. So this is how we compute the tail probability using a hybrid approach, a hybrid between analytic approach and the numerical approach. Okay, now let me conclude. Okay, so here I want to make my talk a little bit broader than the title suggests. So now we are basically in the age of AI. So in the age of AI, and being trustworthy is fundamental, because trustworthy means that we can trust the results given by the AI models or given by machine learning models. There are many different criteria. For example, we need to ensure that the outcome from the AI model should be fair, should be transparent, should be accountable. I mean, if there's a mistake, I know what's the reason. Okay, I should kind of find out the root. Okay, and I also want to make them more robust. But my argument is that the privacy, okay, different privacy is the foundation. Because why? Because only with different privacy, private guarantee, we are able to share the data. Okay, without private guarantee, and we cannot get data what we want. Okay, so that's why privacy is basically the foundation of all these criteria from trustworthy AI. Okay, let me summarize. In terms of informativeness, we can show that the FDP is the most informative through the Blackwell theorem. And in terms of competition, because of the central limit theorem, and we can get tight competition with cheap competition. And with subsampling, and we can also get sharp bound. So our application to the US Census shows that actually we can get about between 15 to 25% reduction in the noise. But the privacy guarantee is not compromised. It's still at the same privacy guarantee. So this means that actually this gain is for free. We don't need to do anything. We just add less noise, make the statistic, make the count more accurate. And we got a media coverage soon after we post our paper in late November last year. So we didn't reach out to the journalists. They just saw our paper on arXiv, and then they interviewed a bunch of people from some census experts from University of Chicago and Harvard. So they praised our work quite much, and especially they think that our result could have an impact on the scheduled 2030 census, because for US Census Bureau, they will do the census on a every 10-year basis. Okay, the next one is scheduled to 2030. So now we are basically working with the US Census Bureau to hopefully they will use our method to add less noise. And so far everything works well because essentially it's for free, right? You just add less noise and get the same privacy guarantee, make your count more accurate, more useful for the downstream applications in politics, in economics, and social science, right? So this is basically the summary, and this is the paper this talk is based on. And basically, FDP is the central part, and this includes epsilon delta DP and the GDP all as special examples. But after central limit theorem, everything will go to Gaussian different privacy. So in this sense, Gauss basically our the one we all, so Gauss is basically maybe the reason we chose mathematics, right? So he becomes a king again. So in the field of differential privacy. And here, and how this is made possible is really because of David Blackwell, because it is the theorem due to Blackwell made the Gaussian different privacy central to the definition of differential privacy. So this means that this is a remarkable agreement between Gauss and David Blackwell. Okay, so the lesson we can learn from it is that although different privacy originally was proposed by computer scientists, but fundamentally different privacy is a statistical or mathematical concept. Okay, here maybe there's another personal story of mine, and I hope to. I first got got a gold medal in Professor Yaw's college mathematical contest back to 2010. So actually, I was very lucky, got a much award, cash award from it, and so I used the cash award to buy tickets and the flight tickets to the US, and I'm really grateful to this opportunity, and also really very excited to see you again. Yeah, and I think this is the end of my talk. Thank you.